Hey guys, welcome to Monkeybox. I'm Agastya, and with me is Sam. In a lot of FIRST Robotics competitions, robots use the shooter to shoot a ball into a goal. Today we'll try and demystify some of the mechanics that go behind the shooter.
For this video, we'll be focusing on the momentum transfer that happens in wheeled shooters, the most common type of which is a hooded shooter.
Let's take a look at a hooded shooter from our 2016 robot, which played the Stronghold game.
It wasn't actually a very good shooter, but that's besides the point.
So let's look at what happens when the ball goes through the shooter.
So when the ball first enters the shooter, the wheel up here will grab the ball and roll it against this hood before launching it out. This all happens in a few hundredths of a second, and we can model the whole interaction as a collision. At the very, very start of the ball entering the shooter, the wheel will be slipping on the ball. But if the ball exits the shooter, and at the end of the shot, the ball isn't slipping against the wheel, then we can model it as an inelastic collision because the surface velocity of the wheel and the surface velocity of the ball are the same. This means that momentum is conserved in the collision, but energy is not. In practice, what this means for the system is that the only thing that's changing during the shot is momentum is lost by the wheel and gained by the ball.
So it looks like what we need to do is relate the linear and rotational momentum of the shooter.
That's exactly right. So this equation can help us explain or help us model what goes on in this inelastic collision. So on the left side, you have all the initial momentums of the system. The main one you have is the initial angular momentum of the wheel. On the right side, you have the final momentum. So you have the final angular momentum of the wheel, as well as the final linear momentum of the projectile. And then, of course, because the projectile is rolling against the hood, you have final angular momentum for the projectile as well. And as you brought up, how do you relate the linear and angular momentums of all of these parts together in one equation? And you have a little model here to try to help explain that in some way. So here you have a wheel that you might see on a shooter. And as the ball goes through, it will roll against a hood and the wheel before being shot out. And during this rolling process, it's only ever in contact with one point on the wheel as it rolls. So the entire inertia of this wheel can be modeled as a single point at a radius pushing sort of, tangentially on the ball to push it out. And in that way, you can relate the moment of inertia of this wheel to a point that can push linearly.
And so throughout the contact time, momentum is being transferred from the wheel to the ball, right?
Exactly. So the important part to pay attention to for momentum transfer is that velocity is being gained somewhere and lost somewhere else. So you're losing speed in your wheel and gaining speed in the ball. Now this is really important for your design process because you need to pay attention to the moment of inertia of your wheel. If you have a tiny moment of inertia, then it's going to have to drop by a large amount of speed to transfer the momentum you're looking for. So this means that you need to speed up to higher than your target speed that you want to shoot the ball at, and then as momentum is transferred, your velocity will approach your target speed. So let's look at how we can apply that theory through math to like a hypothetical example. So up here is the equation that I talked about earlier. So you have, on the left side, you have the initial momentum of the wheel. And on the right side, you have the final momentum. So you have the final momentum of the wheel, the final linear momentum of the ball, and the final angular momentum of the ball. And if you expand out the moment of inertia and velocity terms, then you have some constant in the moment of inertia. You have some mass and radius squared, and then the velocity, angular velocity, expands to velocity and divided by a radius. So you can expand that out for all of those. Now this is very important because in a hooded shooter, the ball is rolling against the hood as it goes. So because it's rolling, the final velocity of the wheel has to be double the final linear velocity of the ball to compensate for that rolling factor. I can substitute that in, so you see over here, substitute it in for the velocities, and then combine all the velocity terms on one side, mass terms on the other, and simplify down to this final equation. Now, why this equation is important is because it gives us a ratio of the velocities compared to a ratio of the masses, and allows us to plug in some hypothetical numbers to see what we would expect out of a shooter. So for all of this, let's assume we want to shoot with a velocity of our ball of 30 feet per second. Of course, that means that our roller, or the wheel, needs to spin at double that, so that's 60 feet per second for this. KB is the constant for the moment of inertia of the ball. So with a solid sphere, that would be 2/5 or 0.4. So this numerator up here is all 1.4. The denominator here, kW, for now let's assume that the wheel is a solid disk, so the constant for the moment of inertia there is going to be 1/2. So that's 2 times 1/2, 1. So 1.4 over 1 times the ratio of our masses. So let's first look at if the mass of the wheel and the mass of the ball are the same. Then you have a calculator here, not that I need it, but you have 1 plus, and then in the numerator you have 1.4 divided by, in the denominator you have 1 times 1, so that's 1. So that's 2.4. So if I want to hit 60 feet per second on the final velocity of the wheel, then I need to shoot with 144 feet per second as the initial velocity on the wheel. That's really, really fast. That's dangerously fast. So let's not go there. Let's add some mass to our wheel, because increasing this value decreases that value. So if we go back, I'm going to clear this. So we still have 1 plus, we still have 1.4 at the top, and then we're going to divide by 1 and then times 2, because we have double the mass in our wheel as we do in the ball. So that gives us a number of 1.7. So times 60 again, we now need to hit 102 feet per second as the initial velocity. That's pretty fast, but chopped off 40 feet per second pretty darn quickly without adding very much mass at all, probably. But let's say for another example, we don't want to add any more mass. We're at the maximum weight for a robot, so we want to find another way to decrease this initial speed, because 102 feet per second is still too fast. So let me clear that. There we go. And another way we can do it is increase this value, the kW. So this is determined by the literal shape of our wheel. So right now we're imagining it's a solid disk. But if we move the mass of the disk out towards the edges, then that will increase that number. So let's say we can change it. It'll never be more than 1, but let's say we can get it pretty close at like 0.8 or so. Then we still have that 1 plus 1.4, and then we can divide by 2 times 0.8, and we keep the same ratio, so that's times 2. And now we're at 1.4. So we got the initial velocity down all the way to 86 feet per second. So we got it from 144 to 86 pretty quickly with minimal concessions in how you actually design it. There are diminishing returns to this, of course. If you make your weight here enormous, you're not really going to affect the initial velocity past a certain point. So it's important to weigh the factors involved in your design and figure out where you want to land on the curve of velocity ratio to mass ratio.
In this monkey box, we discussed the momentum transfer that occurs in wheeled shooters. We went over the inelastic collisions that model the shot, as well as how to apply the theory to help you get a better shooter with less work. That concludes this episode of Monkey Box. See you next time.
How is it, Joseph?